Go ahead and join the Zoom session if you want to. Let's get the waiting room thing. That's all right. I just had just turned it on, so I let everybody in. It's just showing you my picture. I hate that. Let me. Let some people in. It's going to take me a minute, I think, to get everybody admitted and accounted for. So hang on. Okay, again, I'm doing this on the screen so you can tell me if I accidentally count you absent, because I think I've got this, but between looking and seeing, we have a few people who are supposed to be in our Zoom session. Garrett, two. Don't see Matt in our Zoom session. And I think Isaac is here. Okay, I think that's where we are. Oh, wait, our French room. Des made it. Nope. Okay, Verity, looks like you've got one person online and one person missing. Different groups in different states. Check and see. Should be able to find your study group online in some cases. As we move on, let me set this thing to look like a student so I can make sure we're seeing the same thing, and then I'll share my screen. Are we there? How's everybody this morning? You guys all look so good. Are you tired? I'm tired.
Yeah, just a little tired.
I'm tired. I'm tired. Seems like people are, you know.
It's also staying dark longer, and it's getting dark sooner. So now it's going to take a while for my body to adjust to it being so dark and cold in the morning.
Yeah. And it's cold too, so that's pretty sudden.
It is too.
Okay. You guys have been doing great. You're doing great with this new textbook. I think that everybody is having a good understanding of how data fits together, which is what we were hoping with this new book, because our old book we just jumped right in there and started doing syntax, which was great. But then sometimes people don't really have an understanding of how the data fit together. So kind of a big change. I mentioned that before, but as far as our class goes, everybody's doing just an awesome job, and you guys have been doing really good at watching out for everything and watching out for each other. I can tell. Keep it up. I mentioned in the classes yesterday, it's easy for us to start slacking off now at this point. We're in the 4th week, so we're like, this is the end of our 1st quarter of the semester. So we're moving right on through. So remember to keep up with your masks. This kid in my intro to programming class, my husband and I had to order some, over the weekend, and I ordered some of the little metal things to try to do something with these ones with the noses and stuff like that. And so don't forget about that. Keep going, keep wearing your mask and trying to keep ourselves safe, because as I get reports from students about being tested and their test results and stuff like that, it's good to know that everybody's been doing everything they can to stay safe in here. Don't forget to clean up your area before you leave. Each of us needs to do that. So remember, whether you use the spray or the other spray with the rag, either one is fine. I like the no touch spray, but then it makes me cough. Either one is good, but don't forget to do that before you go, and we'll keep ourselves safe here somehow. I forgot to plug in my external yet, but I've got our new chapter up in Cengage. Situated here, and I'm going to go take a look at our modules. I've got some I need to close up. You can tell this mask is supposed to be one of those ones that doesn't let your glasses steam up, and as soon as I breathe, I can't see a thing. So, can't see anything in front of me. Driving while blind. Okay, in my lesson 2, it looks like I have some things I need to complete, but it looks like luckily the instructor hasn't added the prerequisite to where those actually matter, but she could at any moment. So I'm going to go in there and complete them. Just the beginning and the ending. So we're going to be looking at the relational data model, and it's a lot like the stuff that we've been looking at so far. So I think that it'll go pretty smoothly, pretty quickly, because we have talked a lot about most of the topics that they have in this chapter. Just like you've seen so far, kind of a different way to look at things and a different way to emphasize the important points. So I'm going to bring up this overview document just to look at our objectives. And of course, this is just a silly graphic that I found, but here we have a bunch of different objects with our object model, and then our entities being related to each other with our relational model. So we're going to look at that relational database model a little bit more in depth, and some, again, different choices, and look at the characteristics of our tables. Some things we've just kind of glossed over, so we'll get a little bit deeper and add a few more layers here to our understanding, because our understanding is already pretty good. Help if I get to the right place, huh? That one I need to complete. Look at me being so far behind. I'm like, this seems like stuff that we've already talked about. It is. So thank goodness we don't have to do that one again. They're all kind of similar, huh, so far? So we're really moving on to lesson 4, where we should be, and we're looking at entity relationship modeling. So we've looked at all these different models Now we're going to look kind of at the process of building that model and creating that model. And of course, we've been doing that as we go. And you guys have been doing it a lot as you've gone through and done the problems that we've been working on. So when we are working with our entities and our relationships, we've seen already that we have a lot of different modeling tools or diagramming standards that come into play. And we can use those different tools and different diagramming standards at different points in the modeling process, depending on what suits our needs. So we have a lot of different options. Sometimes too, you'll find that you use the diagramming standard that the tool your company bought likes, right? So you might have a certain tool that does all of your modeling, and if that tool uses this 10 layout, then that's probably the layout you're going to be using at your company. So it can have a lot to do with the software that's been purchased. But we're going to really narrow it down. We don't have very many objectives. That's why I was looking at that other one thinking, wait, what? This sounds really familiar. So we're just going to finish this up looking at main characteristics of the entities and relationships. And we want to get into the details of how we can define those entities and kind of work them into our design. And realize that we have some conflicting goals that we have to work things in. So sometimes we'll have people that have different points of view, and it can be surprising how much that matters in our database design. So I've got a link here that goes to your Cengage reading. I have that open because it has a lot of good information. So I want to be able to jump back and forth to it. Now, you guys I know use Cengage a lot. Let me know if there's something that I should be doing that I'm not, or I like using the menu a lot, the table of contents, to move around. And then I'll see other people that don't use that at all, but however you want to move around. One thing that I had not seen earlier is that these appendixes talk about creating entity relationship diagrams and UML diagrams, which we'll look at those now as a retroactive scoring and say, how did I do? I think you guys have done great. Looking at that. So lots of good information. To go along with the reading, I've got the PowerPoint downloaded, and I'm going to open my OneNote notes and get that PowerPoint imported. Oops, wrong one. Steaming. Find the right key this morning. So I'm going to grab my chapter 4 and insert it as a printout. Perfect. So we should have everything in there. We've got our objectives. And when we look at an entity relationship model, which you guys have had a huge amount of experience with already, we have already become aware that we're working with these main components of a database, right? These are our important things. We have entities, attributes, and relationships. So if we wanted to get a little bit more definition oriented, we would say the entity is our noun, right? It's kind of our person, place, or thing. I got to put my text box over here outside of the presentation, and then I can drag it in there, but it won't let me just plop it in. So our noun is our entity, and our attributes we can think of as our has a element, because our noun has attributes or attributes, depending on how you like to say it. So we know our attributes equal our columns or our fields or whatever technical term we want to use for those attributes. And then our relationships are how the things are connected, right? So what should we say there? We'll come back to it. But our relationships are our associations. I wanted to make sure to use the same word between our entities. So I can move those. However you want to make it look. All right, so when we're working with an entity relationship diagram or creating our model, those are the main components that we're going to be concerned with. So let's think a little bit more about that entity. It's our noun. Like I said, it's the object of interest. What are we concerned about? When we're looking at an entity relationship model, we can think of that entity as a whole table, right? So this is kind of a conceptual thing, but if we're thinking about our model, we would be thinking of all the students. You know, I've got all these students in this table. So that's how an entity relationship model considers it. It's kind of a relational environment. But when we're looking at our diagram, our actual physical model diagram, that rectangle really represents one instance. Does that make sense? Because it can be kind of a confusing point when we're designing things. Because yes, we're talking about, as an entity, all of the students. But when I am looking at that diagram and I'm thinking about how does a student relate to a class? Is it one to many, many to many? How does this relationship work? I'm just talking about one of those entities, one of those students. So people can get a little confused in their relationship status and think, well, no, this is many to many because there's a whole bunch of students that take a whole bunch of classes. Well, yes, but we're talking about, we want to narrow it down and zoom in on just one student. You know, can they have more than one class? Yes. So that's what we're looking at. Now they've thrown something at us in this section that in our diagrams, our entity name, they want it to be written in all capital letters. That's a new thing. So I hadn't asked for that before. That's kind of a personal choice. And I don't really care for it. What do you think? When we go to all uppercase, we might as well be all lowercase, right? It doesn't really convey multiple words very well. Their thinking is that if we have all of our entities in all uppercase letters, then they'll stand out in our code or anything that we're using that refers to that entity. So that's why they want everything in all uppercase. So we'll follow their rules. Here's characteristics of an entity. Now these should be highlighted or do something to them in these notes so that they're meaningful to you. Think about each one of these characteristics. If I'm talking about a student as an entity, some attributes of students or characteristics of students, like their name, are required. I have to know them before I can deal with a student. Other things, however, are optional. The domain is the set of possible values. So if I'm looking at, I don't know, a graduation date or graduation year, then the domain of possible values has to be valid years. So I couldn't put something in there like 1, 2, 3, 4. So even though that would be a valid number, it wouldn't fit in the possible domain of values of upcoming years that somebody could graduate. Identifier is something that uniquely identifies one instance or each entity instance, like our student ID. And we've already seen a composite identifier is when that identifier, that unique key, is comprised of more than one attribute, like first name and last name, because that would be potentially an identifier, even though it may not be unique. And then a composite attribute would just be any other sort of data item that could be subdivided. We've seen that, like, I can't even think of any good ones right now. Address and city, state, and zip and all of those kinds of things that could be all put together. And then a simple attribute is what we're looking for, those that can't be subdivided. A single valued attribute is one that only has a single value. And multi-valued are attributes that have many values. So let's look a little bit further at what they mean there. We'll get to it, don't worry. So here is an example of a Chen model. In this model, the Chen diagram shows the attributes. The ones that we looked at earlier, they just kind of gave us the entity name with the triangle or the diamond relationship in between. Here we're adding in the bubbles that are the attributes or characteristics or columns that go along with this entity. So we see we have last name, first name, initial, email, and phone. When we look at a crow's foot model or other type of entity relationship type model diagram, we're seeing the rectangle entity box that we're used to. So how can we identify what our unique key is when we're looking at these different models? Well, in the Chen diagram, we would see an underline under the attribute name of that unique key or primary key. And in our crow's foot, the different entity relationship models that we've seen, we might see an underline or we might see the PK for primary key notation. So the one that they want us to consider here, the majority of these attributes have a single value. If I'm looking at one car, right, my car, then my car only has 1 year, right? That was the year that it was made. If I was looking at a whole fleet of cars, then I would have a whole bunch of years, but I'm not. I'm just looking at one car here when I'm doing this design. So my one car has 1 year. But they're saying, oh, your car can have multiple colors. So they have those 2 lines there. What do they mean? I only have one color. Well, they're like, no, you could have a different color roof and a different color, like upper and lower or something like that. So they're saying this color could actually occur multiple times. You could have multiple values for your car. So I have an exterior color, I have an interior dash color, an interior seat color. So all of those are different color value attributes that are associated with that car. So that makes that a multi-valued attribute. We would think of it, if we were writing program code, we would think of it as an array, right? It's some sort of attribute that repeats for this car, like the color array. And you would say, oh, position 0 of my color array is the exterior color, and position 1 is the interior, and that's how we would do it. We can't do that with a database. We don't get to have those multi-valued attributes, because how many are we going to keep? We have to be able to handle it logically, we can't just have a never-ending array. So what we're going to do is take care of that problem by making those into simple attributes. We can do it a couple of different ways. We could create new attributes, one for each different possible color we could have, or we could create a new entity. So let's think about the first one. If we decided we wanted to make different columns or different attributes for each color field that we might have, we could have a car top color, car trim color, car body color. It would just add all those new columns to our car entity, right? And then we would not have a multi-valued attribute anymore. We would just have a simple single-valued attribute. So that's one way of taking care of the problem. The other way, are they not going to show it to us? Maybe it's in the textbook that they show us. Huh, they don't show us. I thought for sure they show it. So what we would do if we wanted to fix this in the other way, where we wanted to add another entity, is we could add an entity of color. And then we could have a link table where we linked the car to the color entity. And in our link table, we would say this is the top color, you know, and it would be associated with orange and this or that. And then we could have additional pieces of information. Now think about that. If we resolve our problem by adding new columns to our table, we're limited. We can only carry these 3 colors, right? So if we all of a sudden have some engineer that comes up with this great new plan, and now we want to have color in our wheels and the spinners or something, now we don't have any place to keep track of that information, right? We don't have a wheel color. But if we use the new entity approach, where we created a color entity and then we just connected the two, we could really easily just create a new wheel color and put that in as new data in our database. So that would solve our problem without us having to redo the whole database, because now we want to keep track of what color the wheels are. Does that make sense? So think about ways that you can resolve problems like that. Either way, we have to take that multi-valued color attribute and break it down into a simple value. It can only occur once. Okay, and then what are we looking at here? Here we have attribute that's derived. We've got the employee number and last name and first name, initial, date of birth, and age. Which attribute do you think they're talking about when they say it's derived? Hence, it has a little dashed line. What are they talking about? How is that different than date of birth?
Well, age changes.
Age changes. We don't want to carry that on our database. We've got the date of birth. We can calculate the age. So age is a derived value, meaning it was calculated by using other data on our table. And we don't want to carry that kind of stuff. We'll just calculate it as we go. Very good, derived stuff. So we got that. Now, they have a discussion here for us about storing that derived data. They say that there's advantages and disadvantages. So if we have stored that age value, we could actually save processing cycles. So if we were going to process some sort of, I don't know, birthday card app, we're going to send out 7 million emails tonight to say happy birthday to all of the customers whose birthday it is today. You know, maybe we would, in that case, only check the date, so we wouldn't care at all. But if we were going to add to that card and we were going to say, you know, congratulations on your 85th birthday or 14th birthday, now we've got to do that calculation for each of those people. So maybe if we would have just kept that age, we wouldn't have had to worry about it in this massive birthday card thing. So that's going to depend on our company. If we do this birthday card thing and it's such a high priority for our company that we feel like, no, it's got to run faster. It's taking like 15 hours every day to run out birthday cards, and we only have 24 hours in a day. So this thing's going to start running out of time. We've got to figure out a way to make it run faster. Well, we might need to keep that information then in the database. But if we're working for a company who, you know, as a normal situation, doesn't worry about that age that often, then we would be more concerned about the fact that we were going to have to constantly be updating that thing. How do we keep that age accurate? We're going to have to run that update constantly every night too. So there's advantages and disadvantages to keeping that data saved. Now, whenever we don't save it, of course, the advantage is that our accuracy is always going to be up to the minute. We're not going to be dependent on some sort of update process. We can calculate that value right at this moment. But again, it's going to use overhead to do that calculation. So every time we look at something like this, when we're doing our database design, we can think about, you know, advantages and disadvantages. So I like it because there's not really like a right or wrong answer. It's all kind of an art. So you can decide how you want things to be. Now our relationships, we'd seen already that we have a class of relationship that describes our connectivity. So this middle option, our connectivity, we've talked about it quite a bit, that we have one-to-one relationships, one-to-many, and many-to-many in our real world stuff. But some of the other things that we hadn't really talked about is the association between the entities. So in some case, we might have, like a student and a class that are associated in many ways, right? A student attends the class has a list of students, you know, and there's lots of different ways that they can be connected back and forth. So that association can occur in more than one relationship between the two entities. And then cardinality, this measurement that you guys have been using on some of your diagrams already, again, just to define it, we have a minimum and maximum number of entity occurrences within one occurrence of the entity. So think about cardinality here. I could say that the relationship between students and classes requires at least one student, right? Because I can't have a relationship between students and classes if there isn't a student. So I have to have at least one student in that relationship. Now, do I have to have classes? No. So I could have all of these entities exist in my database with only a student who's not actually taken any classes. So I could have one student, 0 classes. What about some others? Let's say I have a person and a car. Can I have a relationship between a person and a car without a person? No, so I have to have at least one. Can I have a relationship between a person and a car without a car? Depends on what I'm looking at, but probably not, because I'm saying this is a relationship between a person and a car. So I need one of them and I need at least one car. Could I have more than one car? Yeah. So I could have a multi-entity relationship there too. So cardinality just says, do I have to at least have one? Could I have many? So whenever I'm looking at that relationship between one instance of this entity and one or many instances of the other, what kinds of minimum and maximums do I have? And we've also talked a little bit about referential integrity, where we said, if I have something like an order that refers to a customer that made the order, that customer better exist, right? Or else my reference is wrong. I have an integrity problem in my database because it doesn't reference properly. So that would be called existence dependence, right? Because I have to have that customer existing before I can have that order. If I didn't have that situation, that would be existence independence, right? I could have an order out there without a customer. We don't see that very much with an order.
I was about to say.
We like them to have customers or someone that's paying.
What would be a good example of existence independence then?
That too.
Because I'm trying to think, and like, I feel like most would be existence dependent, correct?
When we start talking about relationships, then we add that dependence right away.
Right.
But if we're looking at any sort of entity relationship diagram, usually those entities that have the most connections or the most lines coming in or out of them, usually those are kind of our primary entities that we would think of as independent.
Okay.
So to me, it would be like a student, you know, because I could have information about a student without any other information,
Right.
and it would still be valuable student data. So it would be independent of anything else. And that's something that, you know, we're just being aware of as we create our relationship model so that we know we have that dependence or independence. Along with that, as we design, we can kind of solidify that relationship. So if we create a relationship and we have in our relationship our primary key, like our customer key, and then in our order, we have that customer key as a foreign key that points back to our customer. That would be a strong relationship, because if I look at an order, I can find the customer that it's associated with, right? Now, if I didn't have that key, that could be something that could be a problem for us. But we could see that happening once in a while. But in that case, that would be a weak or non-identifying relationship. In one place I might see that often might be some sort of code table. Like maybe I have a table that's all of the lakes in the state, because I use those for building my fishing display. So I have this table of all the lakes, and I might just be able to scan through that table looking at certain information to build a relationship. That, let's see, this area that this person just selected on this map has these lakes. So there is no built strong relationship between this area and those lakes. I've just built it as I've gone on the fly, so that's a weak relationship. There is no identifying data in the table to say this lake is in this area. We just had to deduce it. Oh, I should check. We could have somebody sitting in our waiting room or something. No, yay. Do that if watch Discord in case somebody gets stuck in the waiting room. They can yell out to everybody. Okay, so conditions of a weak entity or a weak relationship. Some things that we want to watch out for whenever we're looking at that weak relationship. The relationship example that I gave you was existence dependent. That means that it was just me selecting that area that created that relationship, right? So it didn't exists outside of that, that means it's a weak entity. What are some other areas where we could have something that is dependent on something else? Our link tables, right? So those link tables that we've talked about creating, they only exist if their parent exists. They're dependent upon that.
So is that, just to clarify in my head, it's link tables, are they always an example of a weak entity? I mean, is that, or would it have to be case by case?
I don't know. I would say case by case just to be safe, but I think they probably would always meet that criteria because we're always using those two foreign keys combined to create our new primary key. So they're always going to have keys that are derived from their parent. So they kind of don't really exist without that parent existing. They're very dependent on that. So. And whenever we're designing the database, we're going to make that decision. I mean, we could carry some sort of key in a table to decide. And when we create a link table, we're saying we're going to create this key by combining these two. So we've in effect said this link table is dependent on both of the parents existing. So our business rules are going to help us make those decisions. Here we have some examples. We have an employee who may or may not have dependents. So whenever I look at my employee, there's always going to be one of them. So that's why my one is up there, right? And an employee can have many dependents. Then we've got all of our stuff listed here. And then our employee, one employee could have 0 dependents, so we can kind of see that relationship. Here's our dependent table. It's totally dependent upon that employee existing, right? We can't have that information stand alone because we have to be able to look at the data in the employee table. Now, a lot of these rules are kind of like you guys were talking about with the different types of keys, the composite keys and the primary keys and all of the candidate keys and everything. And when RJ said they can be many of these, that's kind of what we're looking at here. All of these things are just descriptors that could apply to many different parts of our database design or might not apply. So they're not like one or the other. These are, they're either optional or mandatory, but we might not see all of these different kinds of characteristics exist. So we know the difference between optional and mandatory. Do we have to have a dependent? No, we might not have a dependent. So that's an optional participation. Of course, our given class section may or may not exist for a given course. You guys all know that from trying to schedule. Right? Just because there's a relationship doesn't mean that the class section will exist. But we could change our database design and say, yeah, they have to. We're not even going to create that course table unless there's a section, a class allocated for it. So we could change how that works, basically. We would be using our business rules and kind of influencing them. Okay, let's see if we can clarify these. Help me here. All right. We're looking at the relationship degree. So when we look at our relationship degree, we're talking about how many entities or participants are associated with a relationship. Let me see what kind of pictures they've got. Oh, good. There is a good picture. So I'll move to it. All right. The unary relationship we'll come back to. The binary relationship is where we have two entities that are associated. So in the example here, they're saying that a professor is associated with a class. We've talked a whole bunch about how that could be a one-to-many relationship or a many-to-many relationship. So this is kind of a different way of approaching it, because here we're saying, what is the degree of the relationship? Well, it's binary. That means that anytime I'm going to have this relationship, I'm going to have one of these and one of these, right? So I don't care about how many of them there are just in that relationship. Now here's a ternary relationship conceptual, because we would have to maybe change things a little bit to actually implement this in our database. But let's think about this kind of relationship. Here we have a doctor prescribing a drug for a patient. So all three of those entities have to be involved in that prescription, right? We have the doctor and the patient and the drug that they were prescribed. We have to have at least one of each. Now, to make that into a logical database design, we have to break it down a little bit, again, kind of our link table concept, and add the prescription entity. And as we say this ternary relationship, doctor prescribes patient a drug, we see that we're actually kind of mentioning that that entity should exist there in our sentence when we talk about it. So we add in that prescription, and now one doctor writes a prescription, the patient receives the prescription, and the drug appears in the prescription. Now we still have one doctor, one patient, one drug for that one prescription. That makes sense? That we're talking about the number of entities involved in kind of one instance of our relationship. Okay, so what about the unary relationship? This is where we have a relationship in the entity to itself, to another instance of the entity. So when I look at an employee, in my employee table, I might have an employee ID of the employee's manager. That employee ID would point to another instance of the employee table, right? So I would have the employee table for me pointing to the employee table instance for my boss, right? So that would be a unary relationship. One table, multiple relationships. So whenever we're writing code, teaching programming, the recursive idea, the recursive concept can be a really hard thing for some people to understand. And they always give you guys these awesome math problems is an example of recursion, and then everybody's like, yeah, I didn't really get that and all that. And so it can be really complicated. But if we think about the unary relationship, and they say in a manufacturing process, then maybe it makes more sense. And one way that we could think about it would be a bill of materials. So let's see if we can find a picture of that. Open up your Google. And I want to just try to find a bill of materials list. I'm going to look at images. And here are all sorts of different ones. I'm going to find a good one. How about this second one? Oh, there it is. That's a really good one. It's a laptop. And what I've got here is my bill of materials for the parts that are necessary to build this laptop, right? Because the laptop's been ordered. My company now needs to bring all the parts together to get it assembled. So when I look at a bill of materials, this is a standard structure. First of all, my primary product is this promotional laptop. Within the promotional laptop then is I start my recursive product search of saying, what products do I need in this product, promotional laptop? I see that a battery pack is part of it. And as I go down, I'm finding all these different parts. And another part is a laptop computer. And inside that part, I have a carrying case and a keyboard and all sorts of other things. So the recursive process here is that in my logic, I'm saying, while there are still products that are part of this promotional laptop, keep going out and getting them and bringing them back to me. And when I get to the next product, my code or my logic is, while there are still products, go out and get them. And so I'm going to recursively look for all of the products that are pointing to this battery pack. Then when I finally get done with all of them, I'll move on to the next product. And so my recursive relationship can be built into my product table, where my product table can have some sort of coding that says this part is part of another part, and I can just keep looping through all that information to find that data. So that recursive relationship is going to be found most often when we're looking at some sort of product information. Here's another good one. This one is a little bit simpler. Here, if we want to build product number 1, it's called assembly 1, and it's made up of assembly 3. And assembly 3 is made up of part 1 and part 2. The next thing they ordered was assembly 2, and it's made up of part 3, which doesn't have any other parts, and assembly 4, which is made up of part 4 and part 5. So that recursive structure where I'm saying this is related to another product can keep me looping through all of the different table entities until I've listed all of those bill of material products that are part of that assembly or whatever it is that I'm looking at. They say one common pitfall when we're working with unary relationships is to confuse participating in a relationship with referential integrity. And they are similar concepts, but they are just a little bit different. Because when I'm working with a unary relationship, I'm not dependent. I don't have a reference to another table. Okay, here's the recursive relationship, some other ones. I could have an employee with an is married to relationship. I don't know if I like the idea of thinking of that one as being super recursive. Might make you guys try to implement that. I'm not sure. And an employee management situation. And we could have a course that has prerequisite courses. So we could have a relationship like that there. And you've seen whenever we resolve those kinds of illogical relationships, we can use that composite entry, that link table that connects everything together. So here we have a class and a student, and we know that one class can have many students and one student can have many classes. So we've created an enroll entity. And of course, it has that composite key. So it's a composite entity. All right, so how do we build this entity relationship diagram from scratch, from starting out? You guys have done a really good job. You've been brought in at different spots, been given different pieces of information. What if you were starting from the very beginning? First of all, you would have to create a narrative, a verbal description of how the company operates. Then you'd have to identify business rules based on the descriptions of how they operate. From that, then, you could identify the main entities and relationships from the business rules, develop an initial entity relationship diagram, and then as we're looking at our entity relationship diagram, it's normal for us to start thinking about attributes. What are the columns and fields that are going to go along with this entity? We are going to start identifying the primary keys that describe our entity, and then we're just going to keep reviewing and revising that entity relationship diagram. Let's look at Tiny College here. In Tiny College, after our first go round, let's see what they say here. We've got our professor and a school and a department. And we can look at the relationships here that we've identified. So the school, it's like the School of Business, right? School of Arts. So that individual school is the one that's operating different departments. Thank you, RJ. We've been not having much grouping out there in the hall. Everybody's getting a little bit bolder. So our department code, or our department, if you notice, has a school code to create that strong relationship with that school entity. So we cannot have a department that's in more than one school. We see that business rule right away. And then we can have a professor that could be the dean of a given school. And if we look at our professor entity, we see that there are some fields there, but he is not closely tied to the school blah, blah, blah entity, but the school is closely tied to him or her, right? Because we've got the professor nom in our school entity. So as we're working on it, we add a little bit more. We find out that each department offers different courses. So we start identifying our course entity. We have a unique key of the course code, and we are going to make that a strong relationship. So we're going to add a foreign key of our department code. We're getting some other attributes allocated there. Next, as we're going through our evolution, we decide that a course can be offered as a class in a given semester. So Tiny College here is getting their terminology down for how they want these things to be defined. And when we have a given class, that would be like a section of a class. That class is going to have its own primary key, but it's going to have foreign keys to tie it to the course and the semester that it's offered. So we see that we're building these strong relationships. And then as we do a little bit more design and a little bit more work, we find out that all of the instructors, basically, or a bunch of them, could be considered professors. So not only do we have an entity in our professor table that chairs the department, our department employs a whole bunch of professors. So now we have two relationships going between those two entities. And I point like this because I'm always thinking of the primary and the secondary, or the subordinate in our relationship. Next, we have to add in the information about a professor teaching a specific class. And then we can start adding our student information. So for students, again, we have a primary key, and we're going to say that a student can enroll in a class. So student is written in enrollment, and enrollment is found in our class. And then finally, we're going to say that we are going to assign departments to students. So based on what their major is, we're going to put them in a certain department code. And that could be a risky move, huh? Because students move a lot, but that's all right. We've got to associate them with something. And then we can say that, oh yeah, besides professors being part of a department, they might also be advisors of students that are in that department. So we could have that relationship too going on besides the class. And then we could add in some overhead information and say, well, classes have to have a specific room and rooms have to be in buildings. So now our support information and our support tables start coming into play. So these entities are really important to us, but we can see where they're not as critical is the primary entities that we are concerned with in our database, but they're very important. Now, as we go through, we could make a list of all of our entities and their relationships and connectivity status to other entities. And this is just a good check to make sure that everything is in place, nothing is missing. Now, as we're working on our design, we're going to have to make compromises. We have to conform to design standards. So there's certain things that we just have to do. We might be adding too much overhead. So even though we have really, really fast computers and all that great stuff, we still might want to limit our complexity a little bit and make some of those logical relationships that we would like to have. We might have to enforce those more programmatically instead of putting them in the database. So we want to make sure that we're taking into consideration our performance. And then we want to make sure that all of this data isn't slowing things down overall. Sometimes we can add in a database and the employees that are using it can be overwhelmed with all of the data that they have to enter, but it's not worth it to them. We'll see what we got here with this one. We've got an employee, and we started out with this kind of spreadsheet where we have the employee and then we have a spouse employee number if they're married. And then we decided that we should split that out and we should have a different table that just shows us employee number relationships. So employee 345 has a spouse of 347. And with our self-joining link table like that, that's giving us that relationship information and pulling it out of this main table, so that's good. And then we think, well, you know, we could do some other things. We could add in an actual marriage entity and say that each time someone in our employee gets married, we add in this marriage as a unique key, and we keep track of what the employee number was and all that information to keep track of it. So what are our conflicting goals in this situation? We knew at the very beginning that our employee table up here could yield to anomalies because we could have a divorce, right? And then we could have some problems with our data or something like that. So in the second implementation, they say that eliminates the problem of having null partner IDs in some of our rows, but it doesn't really take care of the problem of duplicates. If somebody gets divorced or something, we'd have to do some cleaning up. So the third approach, they say, where we add our marriage and marriage part, we've got these new entities. This approach does have issues though, because it makes us get additional data from the employees. Do you see that right away? So now we might be getting a little too personal so even though as database administrators, we're like, well, this is a really valid data representation of how we want to keep track of this information. Are we building ancestry.com here? You know, is that too much information to ask from an employee? Yes, it is. So we have to back off a little bit on some of our design based on that kind of information. So we can't keep track of everything that we would like to keep track of because sometimes we have privacy issues. So lots of different solutions there. All of our different solutions would require some sort of programmatic control of this relationship on top of what the database management system can do, because we know we have to go all the way to this marriage entity to get it to be programmatically happening automatically. And we've just decided that we can't do that. So we're probably going to have some programmatic control built in. And we can do that in the database. We can create what are called triggers that will run at certain times to make sure that we have all that information kept intact in the database. But as they mentioned in our textbook, because we're going to need to do that, we need to document. So part of our design is documenting that information, and our model does a lot of that documentation for us, but it does leave some that we still have to do in another place, like notes like that, other things that we're going to have to take care of. Oh, awesome. Okay. I was hoping we could kind of talk about that whole section. So on Thursday, we'll do something a little bit different for our first part of Class Good. We won't have to look too much at any content. And that gives you some time. I think from looking at grades, it looks like people need to finish up the problems from chapter 3, and that should be fine because we shall have an hour or so next time of lab to do the problems from this one. And I'm going to figure out how to grade the problems from chapter 2 while you guys think bad things about it. Use a new one. Any questions? Lots of the more same. We're going to start making some databases here in a minute. All right, I'm going to stop this share and let everybody get all of their great problems done. Let me know if you need anything.